Hello everyone, and welcome back to the Shimadzu Introduction to Liquid Chromatography series. Today's webinar will build on the knowledge gained during session 1. As such, today's session will explore different types of liquid chromatography, specifically how separation occurs. We will also touch upon other factors used to improve our separations. This series of webinars continues from our last session entitled Fundamentals of Liquid Chromatography, with today's session looking at types of separation we may come across and how these separate our compounds. We will also touch upon some effects used to improve the separation. Our future sessions will include topics such as building your method or method development, UHPLC, instrumentation, optimizing your method and instrument, and troubleshooting of data and common issues. So let's begin our session today with a brief recap of our first session. As part of the last webinar, we learnt that the inside of a liquid chromatography column is packed with particles, usually silica in nature. These particles in modern columns are spherical and uniform. The inside of these particles is like a network of pathways, similar to the structure of honeycomb. Along the outside of these particles, as well as the walls of the pathways, are compounds known as functional groups. These functional groups create an environment that promotes interactions of the compound, enabling separation. These functional groups could be different, such as C18 or phenylhexyl. The choice is dependent on our samples. The stationary phase includes both the silica bed and the functional group. Our compounds differ chemically. This difference in chemical nature will create the attraction to the stationary phase in differing amounts. This leads to separation as a function of time. A quick reminder visually. This showing the separation of our compounds and the resulting detector response, known as a chromatogram. As we see, the separation is occurring as it travels along our column. So, having recapped on our last session, we will move on to the first part of today's content, types of liquid chromatography. We will cover 4 major types of liquid chromatography. These will be ion chromatography, size exclusion, normal phase, and reversed phase. As part of each of these types of chromatography, we will look at what types of columns we will use, as well as how separation is achieved. As we mentioned in our first webinar of the series, all separation types require some form of interaction, or indeed lack of interaction, with the column stationary phase for the compounds in our mixtures to separate. Most types of liquid chromatography take advantage of interactions such as the charge on the compound, size or hydrodynamic volume, or the polarity of the compounds. So our first type of chromatography we're looking at is ion exchange. This utilises the charge on our compounds to promote the attraction or repulsion from the silica base of the column. These attractions can be weak or strong, as well as anion or cation based. Our mode of separation exploits electrostatic attractions and repulsions. Using the opposite charge for our compounds increases interactions, creating separation. The degree of separation is governed by the charge's attraction, the size of the charge, and the size of the molecule itself. pH and salt concentrations of our mobile phase can also alter the electrostatic interactions and thus the separation. Looking at our separations, we can split them into 2 categories. First is anion exchange, where our compound of interest is negatively charged and any positively charged compounds will be repulsed by our positively charged surface, whilst negatively charged will be attracted. This creates separation between the two types. Second is cation exchange, where our compound of interest is positively charged. Any negatively charged compounds will be repulsed by our negatively charged surface, whilst positively charged will be attracted, again creating separation between the two different types. Knowing that anion exchange creates separation of negatively charged compounds, we can now look further at how it would separate different anion compounds. Separating fluoride, chloride and bromide, the elution order would follow the relative size of the ion, the smallest ion size having the weakest interaction and therefore the first eluter. Separating nitrate, phosphate and sulfate would work in the same manner. Studying the cation exchange creates separation of positively charged ions. Separation follows the same rules as the anion. Separating zinc, silver and aluminium will be done with the size of the charge. The higher the charge number, the stronger the attraction to the stationary phase, and thus longer time to pass along the column. Separation of potassium, sodium and lithium is based on the size of the ions. The smallest, lithium, can reach into spaces the others are too large in size to reach, thus spending longer to pass through the column. Our next chromatography type is size exclusion chromatography. These columns are usually polymer or silica, whose pore size is such that separation occurs due to the hydrodynamic volume or size of the compound. The mechanism of separation works similar to a sieve. The column has a select range of size pores. As larger particles cannot pass through the honeycomb-like interior of these pores and particles, they pass along quickly, therefore eluting first. Smaller particles can travel throughout the whole particle network of pathways, taking longer and eluting last. Let us look at this visually. Taking our sample, we would introduce this into the system through injection. Our particles have various sizes from large to small. The large particles cannot fit through the honeycomb structure of the particles, therefore passes around the outside, passing quickly. Medium-sized particles are able to pass through some of the pathways, but not all, therefore taking longer than the larger particles. The smallest particles shown here can pass through all the pathways as well as around the outside, therefore taking longer than all of the other particles. Due to the size difference, altering the time taken to travel through the column, the different sizes will then show separation. As the small particles can take the longest, variation time is bigger. Therefore, as well as seeing a later eluting peak, they are broader. This is commonly seen within isocratic liquid chromatography separations. How can we optimise the separations further? Well, let's take a look at a single particle, expanded. The pore sizes can vary in size. We can look at how we can use the pore size to aid our separation. Our largest particle here will pass by all of the pores, whereas A and B have a small amount of interaction, while C has an awful lot of interaction with the pores. This similarity in interactions between A and B leads to the peaks overlapping. Whereas if we change the size of the pore even slightly, the largest particle will still pass by. But now there will be more interaction time between compounds A and B with each particle that passes, leading to a separation of the two peaks. Our next separation is normal phase chromatography. This is the oldest of the liquid chromatography types, used by Svet more than 100 years ago to separate colorants within plant material. Today's columns still use a silica base which can be bound to small functional groups to promote attraction. The separation in normal phase uses mobile phase that is 100% solvent. Separation draws upon the difference in polarity, with the most polar being attracted towards the stationary phase. Less polar compounds have limited interactions with the stationary phase, thus eluting first. These hydrophilic interactions revolve around the silica stationary phase. In this example, we have 3 compounds that we will study to look at the strength of interactions to best understand normal phase chromatography. Here we have structure 1, which is benzene. This will have very weak interactions with the stationary phase in normal phase chromatography. Structure 2, phenol, shows the addition of the alcohol group, increasing the strength to have strong interactions. Structure 3, 2,6-diisopropyl 4-methylphenol. Well, this also has an alcohol group, so does this have strong interactions as well? Unfortunately, this is not the case. It will actually have weak interactions due to the steric hindrance from these functional groups. So our structures had a very weak, and a strong interactions, and therefore will elute in the same order. Our final type of chromatography we will look at is reversed phase. This is probably the most commonly used form of liquid chromatography separation. This type utilises a non-polar stationary phase and a polar mobile phase, the opposite of our normal phase example. Ligands attached to the silica base can vary, such as PFP, aminyl propyl, but most commonly is C18 or ODS. Separation occurs utilising the difference in polarity of stationary and mobile phase. The less polar the compound, the earlier it will elute. Reversed phase chromatography utilises hydrophobic interactions. These revolve around the functional group, in this case a C18 or 18 long length carbon chain embedded upon the silica base. Our example compounds here will have different strength interactions with the stationary phase functional group. The phenol within our normal phase example had strong interactions with the stationary phase, compared here to the reversed phase where it is weaker than the normal phase and weaker than our second example compound, toluene, which has a high carbon content compared to phenol, creating stronger interactions. These strong interactions in comparison will create a difference in the separation, with the phenol eluting first and the toluene last. During session 1 we studied how the LC column worked. We have now seen how this knowledge can be adapted for different types of chromatography. In the second part of today's session we will build this knowledge with the topic of effects on separation. So during session 1 and so far during today's session we have established how different techniques separate our mixtures. What happens if these interactions only partially separate our compounds? What other techniques can we use to change our partially separated compounds to fully separated? Firstly, we will look at a 50-50 solvent composition. Our molecules will interact with the mobile and stationary phase. However, the interactions are too similar to fully separate within our resulting chromatogram. Here we can see that they are not fully separated. Moving along our solvent composition ratios from 50-50 to 30-70, and thus the additional water, the compounds will now interact differently with the mobile and stationary phase. This in turn alters our separation to create 2 separate peaks instead of the previously merged peaks. Utilising a real-life example, we have 3 compounds eluting at almost identical times, showing no definition and definitely no 3 distinct peaks. So in changing the solvent composition to a lower solvent ratio, we can now see that there's 3 peaks, but they are not separated, which is the result we're looking for. Moving along to 30% now, a lower ratio still, with a larger amount of separation between the compounds, but not fully separated. So if we move just a small amount now to 25%, we will achieve a separation that we would be happy with to utilise. Please note, as we reduce the solvent from 50% top left to our final result, 25% bottom right, the peak at the initial time moves from 2 minutes to 12 minutes, showing that our compounds are separating by being retained longer, so therefore elution times also increase. The second effect we will look at is pH. Control of pH. This can aid our separation in a similar manner to solvent composition example. This, however, is paramount for certain compounds. The adjustment of pH changes the chemical environment. As we know, changes to the chemical environment alter separation and retention times. pH control is great for compounds that ionise. Ionisable compounds are those that can chemically alter enough to accept a charge. We have an example here using acetic acid. It has ionisation centres. We have the neutral molecule, as seen in both diagrams, as well as the negatively charged oxygen. These produce different ionisable results, known as acid dissociation constant results. In order to alter the retention of the compounds, we can alter the pH. So what effect does this have when changing the pH? We can map the amount of each ionisable state of acetic acid as we change the pH from low pH to high pH. Compound A will start at high amounts and compound B will start at lower amounts. As we move to higher pHs, these amounts change to have less of A and more of B until they are completely reverted. This stays that way for the remaining change to higher pHs. As we can see, the change from low to high changes the percentage of each species. This change is what we require in order to separate the compounds and their different affinities to the stationary phase. We can also affect the separation controlling temperature, our third effect. There are several reasons for controlling the temperature. Using a column oven ensures that the whole column is at a constant maintained temperature. This prevents any laboratory temperature fluctuations throughout the day, causing any deviations within our chromatograms. If we were running samples over an entire long day where the laboratory temperature fluctuated by several degrees and we didn't use a column oven, this would lead to 2 different chromatograms at the beginning and end of the day. But are these the same? If we overlay the 2 chromatograms, we can see that they are not identical. And having no column oven has led to deviations within the retention times, which may cause incorrect compound labelling, especially with close eluting peaks. Alternatively, within the same laboratory, we can use the same analysis using a column oven this time to negate those fluctuations in laboratory temperature. Therefore, taking samples run at the same time as we saw before, we can now look to see if these are the same. The result is chromatograms that are so similar that they look as if there is the presence of only one chromatogram, showing the increase in control using a column oven and a reduction of variance in our retention times. As I mentioned earlier, there are different types of ways in which temperature can be used. We have looked at using the column oven to negate laboratory temperature fluctuations, but how about using temperature to change the fluid dynamics of our mobile phase. When these change, the speed of interactions will also change. As with all other factors, changes in these interactions alters the elution time and thus separation. We can look at this visually. Utilising the same timescale, we have our initial chromatogram. As we increase the temperature, the compounds will increase in their mobility and elute quicker. This increase in time travel will then lead to a decrease in the time that the first peak is seen. This decrease also creates a narrower peak due to the same time difference. As the number of particles that creates the peak is the same, the area must match in both chromatograms. We have already said that the peaks are narrower, therefore, to have the same area, the peaks are also taller in our higher temperature chromatogram. As we increase the temperature further still, these changes increase yet again, to leave our final chromatogram at the highest temperature having 6 compounds eluting within the same amount of time as our initial 3 components. So what is the outcome that we are trying to achieve? With all things, we're trying to get the best separation for our compounds that we need and find the best ratio of factors. How do we know when we have got the best conditions? What will the chromatogram look like? When we start developing our method, we may have a jumble of peaks that are closely eluting or even co-eluting. This dramatisation shows the optimisation process, whilst altering various conditions of things such as pH or temperature, solvent composition, and even functional group of the column. The peaks begin to separate into clearly defined individual peaks. Further optimisation can then be carried out to shorten the overall time of our analysis, whilst maintaining elution order and relative separation, known as efficiency. We will cover this within some of our future sessions. So the summary of today's session. LC has multiple types available for different compound analysis. The most commonly used are ion chromatography, size exclusion, normal phase and reversed phase chromatography. Separation occurs in all of these types of chromatography and utilises that difference in interactions between the compound, the column and the mobile phase. When we have separation of our compounds, we can further improve it with other conditions such as solvent composition, pH and temperature control. What we are trying to achieve is a method that produces fully separated compound peaks in a suitable time. This method would be consistent and reliable to achieve the best data. If you are finding these webinars helpful, then visit our website for other webinar series that might also be helpful for you, such as cannabis analysis, liquid chromatography purification, gas chromatography, and method development of LCMS. Please visit our website www.shimadzu.co.uk/webinars for these and other webinar series that are open for registration or available on demand. If you'd like to hear more from Shimadzu, please do join our mailing list. You will receive all the news and product development from us. Look for the link in the follow-up email or go to our website www.shimadzu.co.uk and click on e-news located at the top of the screen. You can find us on all the usual social media platforms. Please feel free to contact us should you wish to find out more. That's all for today. Thank you very much for participating and enjoy the rest of your day.
Excellence in science. Shimadzu.